Hi everyone. So today we'll be discussing on the topic Howard's minimum cycle mean algorithm, right? As I've said earlier while discussing this one Karp's algorithm. So Karp's algorithm and Howard's algorithm say solves the same problem but in a different way. The implementation will be little different, and Howard's algorithm is little bit faster than the Karp's algorithm. Yeah, let's see what the definition part says here. Howard's minimum cycle mean algorithm, also called as policy iteration. Usually we call it as Howard's policy iteration algorithm itself. Yeah, you have to remember this name at any cost. Yep, Howard's minimum cycle mean algorithm, also called policy iteration, for the minimum mean cycle. Yep, what it does, it finds the cycle in a directed weighted graph. So it is applicable only to the directed weighted graph. Yeah, it's not applicable to the undirected graph. Just remember this one at any cost. Yep. So Howard's minimum cycle mean algorithm finds the cycle in a directed weighted graph whose average edge weight is minimum, right? Whose average edge weight is minimum. Similar to the Karp's algorithm, we will be taking the minimum from the cycle that we have, that we will be deducting. Actually, you'll come to know when we write the algorithm rather than explaining it now. Yeah. Now let's move on with the further things. Instead of checking all the cycles, it iteratively improves the policy. What it does, instead of checking for all the cycles, so in the Karp's algorithm, usually what we did, we basically the algorithm stated that, or through the algorithm we found all the cycles and then we got the minimum, right? So we got the value from each cycle by total weight by number of edges present. Then we chose the minimum value among the values that we got. Yep. So here, instead of checking all the cycles, it iteratively improves the policy, right? Nothing but one outgoing edge per node until the minimum mean cycle is found. So it's as simple as that. Now it's okay if you didn't get everything. So we will be discussing the approach or the algorithmic part, and then we will be moving towards the coding part. First, as I've said, we will be, let's move on with the this one algorithmic part or the approach part, right? So let's do that. So here, what happens? This is the algorithm, or the, sorry, this is the graph that we'll be going with actually. Yep. So this is fine, I believe. Just look at the graph. I insist you to pause the video and have a look into the graph first. So graph is from here to here, right? So we have certain edges as we are going with the Howard's algorithm. So we will be going with a directed weighted graph itself, right? So we'll not be dealing with a undirected graph. So from A to B, we have the weight 3. From B to C, we have the weight 2, and from A to C, or C to A, sorry, we have the weight 4, right? From B to D we have 1, and from D to B we have 1 as well, right? So this is the graph that we'll be going with. I insist you to, again, I insist you to pause the video and have a look into it. Yep. Let's move on with the further things. So first step here, uh, as the name itself indicates that we will be dealing with a policy iteration. Yeah, it's called as Howard's policy iteration algorithm mainly. Yep. So first step, what we'll be doing, we will be initializing the policy. When I say we will be initializing the policy, we'll choose one outgoing edge from every node. Yeah, we'll be choosing one outgoing edge from every node. See, suppose the example accordingly with the graph that we have considered, A to B. So this one, A to B. This is the outgoing edge, right? So B, this is the incoming edge, right? So we have the arrow mark here. And C is also the outgoing edge, C to A. So B to C, this is also outgoing edge. B to D, so where B is the outgoing edge, yeah. From D to B, again D is the outgoing edge, right? So like that. So these are the examples. You can just pause the video and have a look into it. Next, this policy forms a cycle. This part, A to B, B to C, and C to A. You can clearly see here, A to B, this one, A to B, and then B to C and C to A. This quite obviously forms a cycle entirely, right? So just give me a second here. Yeah, A to B, B to C, and C to A forms the cycle. Yep. So this part, yeah, this completely forms the cycle as it is directed graph. So mean weight would be, so we have to calculate the mean weight at any cost, right? So it will be total weight by number of edges that has been found, that we have actually. So number of edges we have is A to B one edge, B to C one edge, and C to A one edge. 3 edges we have. Total weight is nothing but 3. Uh, 3 plus A to B, we have the weight 3. So this will be 3. B to C, we have the weight 2. This is nothing but 2. And C to A, we have again 4. Right? So this one will be 3 plus total weights by number of edges. 3 plus 2 plus 4, nothing but 5 plus 4 is nothing but 9. 9 by 3. And this would lead to 3. Yeah, 9 by 3 would lead to 3. So this is what I have written. Mean weight would lead to 3. Yep, it's as simple as that. Now let's move on with the second step, nothing but we have to evaluate the policy now. Yep, we have initialized the policy. Now we have to evaluate the policy. Within the evaluate policy, this one, within the evaluate policy, what we'll be doing first, we'll be calculating the potential values. Yeah, so we have to calculate or compute the potential values in the sense distances. Yeah, that we'll be seeing, right? So you don't have to worry about it. Just remember that we'll be calculating the potential values. Yep, for the nodes using the cycle mean. For the nodes using the cycle mean. Yep, this tells us whether switching edges can reduce the cost or not. This tells us whether switching edges can reduce the cost or not. Yep, so this is fine. Next, let's move on with the improve policy. Yeah, step 3, nothing but improve policy. We are done with the evaluate policy. Now we will be moving on with the improve policy. In the improve policy, what we'll do first, we will check each node. Yeah, so we have 4 nodes, right? A, B, C, and D. Right, so we have 4 nodes. We will be checking for the each node as we need to improve the policy if possible. Yeah, if possible, right? So this is also one of the step we have to this one involve this particular step. If possible, we need to improve the policy. For that, we will be checking each node. If another outgoing gives the smaller reduced cost, switch policy. In the sense, see here, suppose here we have from D to B. See, B to D we have and D to B we have. We do not have the two edges. Suppose if we had B to C and the weight was 1, we will be choosing B to C with a weight 1 itself. Yeah, that's what improve policy this one says actually. Yeah, we will be checking for each node. If another outgoing edge gives the smaller reduced cost, in that case we will be switching policy or we have to switch the policy. It's as simple as that. Yeah, so we are done with this part. Simple example is B to D instead of B to C. So this one as well, right? So we have this one, what do we call, B to C, we have the weight 2, and B to D we have the weight 1. Instead we can choose for the B to D itself, right? So this also we can do as we are considering the complete graph actually. Yeah, so this is fine. Now if when we choose B to D instead of B to C, so this one will be B to D to B again, right? So this one will be B to D to B. So this part, this completely forms the cycle, you can clearly see here, right? So now we have 2 edges. Yeah, we have 2 edges, total weight by number of edges, right? So B to D edge has 1, the weight 1, and D to B has the weight 1. So this one will be 1 plus 1 by 2, nothing but 2 by 2. Here in this case mean will be 1. Yeah, mean will be 1. So this is fine. Yeah, next let's move on with the repeat. So we will be moving on with the same process, or we'll repeat the same process. Yep. So see here, we'll continue improving policy until no better edge exists. Again, we'll continue improving the policy until no better edge exists. Yeah. So this is what we will be doing. So just to improve the policy basically mainly. The final cycle will be B to D to B, because this is the minimum mean cycle. Because see here, so we will be choosing this one, the minimum value from the mean that we got, right? See, we got 3 here. One cycle that we had found was A to B, B to C, and C to A. We got the value 3, right? And another one here, the last one. So this one B to D to B. So this one we got mean 1 here, right? So out of this one, we have to go for the smaller one. So this one will be min of 3 comma 1. So we will min of 3 comma 1 is nothing but 1, right? So minimum value is 1. So we will be displaying this one as the output. We will be choosing the minimum value as always, right? So yeah, mean will be 1, and this is the minimum mean cycle that we have considered. So output will be 1 here, right? So the output will be quite obviously 1. If you can't see it, let me write it over here. Mean will be 1. So this is it for the algorithm. It's as simple as that. If you know the corpse algorithm pretty well, So implementing the Howard's algorithm will not be difficult. Code will be little bit lengthier because we'll be going with a policy iteration. You might find little bit lengthier, but if you would have understood the Karp's algorithm, understanding the Howard's algorithm will be a piece of cake. It will be easy, I assure you. So that is the reason. If you hop into, it's vice versa. It doesn't matter if you are going with the Howard's algorithm first. If you would have understood the Howard's algorithm, you will understand the Karp's algorithm easily. But Howard's algorithm is somewhat faster than the Karp's algorithm, right? So implementation is a little bit difficult. I won't say difficult. It's little bit lengthier than the Karp's algorithm, but Karp's algorithm is easier to implement rather than the Howard's algorithm. But Howard's algorithm is somewhat faster than the Karp's algorithm. These points you have to remember at any cost. Now we are done with the approach or the algorithm part. Yeah. So we are done with this part. Let's do one thing. Now let's write the code. If everything goes well and if we get the desired output, let's consider the same example that I've considered for the approach. I'll be considering the same example, right? If we get the desired output, then we can just move on with the complexities part. Yeah. First, what we'll do, let's write the code. So let's do one thing. Let's move on with the algorithm part. Yep. First thing, I'll do one thing. So we'll be making use of the input output. So I'll just input output this one. Let's import input output package actually. Yeah. First, let me import utility package. Will be making use of different utilities as well, right? As well as the input output. So I'll just go with Java. Yeah. So this is fine. Yep. Now within the main method, so or within the class, this one, Howard's minimum cycle mean algorithm class. So first thing what we'll be doing, let's go with the main method itself. So I'll just go with public here, static void main. So yeah, this one itself. So let me make use of throws exception or else we'll be getting the error. Yeah. Yep. So this is fine. So first thing, I'll be making use of the buffered reader and the print writer. So this is completely related to the input output, right? You can ignore for now actually. Yeah. So BR will be a new buffered reader, new input stream reader of system.in. And same thing, let me go with the print writer as well. Either you can just go with the this one. Sorry. Yeah. Out equals new print writer system.out. So this is fine. Yeah. Next. Mm, so accordingly with the example that we had considered during the approach, so we had four vertices. Yeah. A, B, C, and D. So I'll just go with n equals 4. Either you can consider n or v. It doesn't matter, right? N is nothing but nodes. A node or the vertex is same, right? So n equals 4. So this is fine. Next, let me go with this part. So int mm, 2 equals. So what I'll do here, so let me go with 1. Let me go with this one. What do we call? Let me go with 2, 3. Let me go with 0. Yeah. And let me go with this one again. Yep. So this is fine. So node 0 has an edge going to the node 1. Node 1 has two outgoing edges, C of 2 and D of 3. Node 2 has an edge going back to the node 0. And node 3, nothing but the D has an edge going to the node 1. We have already discussed this one. Yeah, I have already shown you the graph. You can just go to the that part of the video and you can just see the graph, or you can just watch that part of the video and come back. Yep. So this is fine. Yeah. Next. So let's do one thing. I'll be going with int w equals. So let's consider the weight actually. Let me consider 3 here. This is fine. And then let me consider 2 comma 1, and let me consider 4, and finally I'll be going with a 1. So this is fine, right? So weight of the edge A to B is 3, weight of the edges B to C is 2, and B to D is 1. So I have already shown you the graph. Please do, if you are not understanding now, the same example that we are writing it in the form of code. I mean, we are just articulating the same thing in the form of code. You can just watch that part of the video where I have shown you the graph, and you can just come back here, right? So this is fine. And finally, this weight of the edge C to A is 4, and so this one is 4 actually. And finally, yeah, weight of the edge D to B is 1. Yep. So this is fine. So let me come out of this one entirely. Now, the first step, if you remember, we have to go with a policy, or we have to deal with a policy. So I'll just go with a policy here. So this one will be new int of n. Yep, so this is fine. So this is the policy array where we'll be storing the outgoing edge, right? Each node uh, currently chooses. So this is fine. Let me go with the policy of 0 equivalent to 0 initially. So we have 4 vertices, right? So we have to do the same thing. Let me do one thing. I'll just copy the same thing here. Let me paste this one thrice and make the necessary changes here. So policy of 0 is fine. Policy of 1, policy of 2, policy of 3. Right, so this one, the value will be 0 itself. See, node A selects its only edge A to B. Node B initially selects B to C, index 0 in the adjacency. Node C selects C to A, and node D selects D to B. Right, so this one we know. At this point of time, we should be knowing this. Yep, so this is fine. Next, I'll just go with the Boolean. So let me make use of the variable improved here, and let me assign this one to the Boolean value true. So this is the flag to track if the policy improves during the iteration. Yeah. Next, let me go with the while condition. While, let me go with the improved. So this is fine. Uh, 1 second. Yeah. So within the while loop, so we will continue the policy iteration until no improvement happens. So I'll just go with the improved equals false. So this is fine. Next, what we'll do, so we have to compute or calculate the mean weight of the cycle formed by the current policy. So I'll just go with a double here. So this is fine. I'll just go with best mean equals, let me go with find cycle mean. So we haven't written the find cycle mean method yet. Let's do one thing. Let's write the find cycle mean method first. Yep. And then later we can make use of it. Yeah. Right. So I'll just go with this one static uh, double. So I'll just go with a find cycle. So let me go with the mean. So this one will be int policy. So let me go with int. So this one too. Int. So this one will be w, nothing but the weight. And finally, I'll just go with the int n. Yep. So within the method find cycle mean, first thing I'll just go with the Boolean. So this one, let me consider the visited array itself, as we need to mark the visited array, or visited array is required to detect when the cycle is reached actually. Yeah. So I'll just go with the visited VIS. So this one will be equivalent to new Boolean of size, and it depends on the number of size depends on the number of nodes we have, right? Or the number of vertices we have. Next, I'll just move on with the for loop. So this one will be int I equals 0, I less than n. Let me increment the I. So within the for loop, what I'll be doing, let's consider the current node pointer. Here in this case, I'll just go with current equals I. So this is fine. So after considering the current node pointer, we have to reset the visited arrays for the new traversal, right? That we have to do. The nodes that we have already visited. Yep. So I'll just do one thing. Let me go with the arrays dot fill. So I'll just go with the visited here, and let me initialize everything with a false, right? We are just resetting the visited array for the new traversal. Next, let me go with some. Let me initialize this one with a 0, and let me initialize length to 0 as well. Yep, sum equals 0 is nothing but the sum of weights on the cycle. Length, the variable length is nothing but the number of edges on the cycle. Now, let's move on with a standardized while loop. Standardized while loop in the sense, while not of visited of current, this one. Yeah. So what I'll do within the while loop, first thing, so we have to continue until we revisit the node, in the sense until we find the cycle. Just give me a second here. Yeah, until we find the cycle. First thing, we have to mark the current node as visited. For that, I'll just go with the visited of current, this part. Let me assign this one to the Boolean value true. It's as simple as that. Now, after successfully marking the current node as visited, we have to get the edge that is chosen by the policy for this particular node. I'll just go with P equals policy of current itself. Yeah, this is correct. Yep. Now we have to add the weight of the selected edge. For adding the weight of the current edge, so I'll just go with W of current. So this one and P. Yeah, so this is fine. I'll just go with the current equals to this one will be current and P. this one. Yeah. So this is also fine. So we just have to move to the next node following the policy edge. Finally, we have to increase the cycle length counter. For that, I'll just increment the length. Yeah. This is it for the this one. This is it within the while loop. Let me come out of the this one while loop entirely. Now we have to compute the average weight, right? Average weight. This is same for Cobb's algorithm as well as the Howard's algorithm. So average weight is equivalent to the total weight divided by the number of edges that is present within the cycle that we have considered. Yeah. So accordingly with the code that we have written, so this one will be written. We have to return double, right? Sum by length. Yeah, this is correct. Yeah. So this is fine. Finally, I'll just come out of this one entirely. Um, Somewhere I have done something wrong, man. I don't know what I have done wrong. Or anyways, so I don't think I thought I misplaced brackets. No, this is fine. This is correct itself. Finally, we have to return very large value if no cycle is detected. If we haven't found any cycle, in that case, let's this one. What do we call? Let's return very large value, right? So I'll just go with return. So let me go with double here. Dot max value. So let me give this and change the min to max here, right? We are returning max value, not the minimum value. Yep. So this is fine. We are done with the find cycle mean method. So let's do one thing. Let's copy the same thing and make use of it here, right? So where we were actually here. Basically, we were computing the mean weight of the cycle found by the current policy, right? So for that, we wrote the method find cycle mean, right? So let me paste this one over here. And what are the parameters that we have to include? So here we have policy. So let me copy this one and paste it over here. And we have two, and I'll just go with the 2 as well. So I need W as well as the N we have. So let me mention W and N. Let me type this one. Yep. So this is fine, man. Next, let's move on with the for loop. So I'll just go with the for here. Int I equals 0. I less than N. Let me go with I plus plus. So within the for loop, what we are doing here, first of all, we are iterating through the every node just to check the possible improvements that we can do. Accordingly with the algorithm, we have to improve the policy if it is possible, right? So I said during the explanation of the algorithm, I said this step is necessary, right? So if we have found the better policy, so then in that case we have to update the value, right? So within this one, I'll just go with a one more for loop. We'll be going with a nested for loops. Yeah. So let me go with j equals 0. J less than here, instead of n, let me change this one to 2 of I. Yeah. So this is fine. And we have to consider the length of this one, right? So let me mention length as well. So this one we will be incrementing the j. So this is fine. Next, within the for loop, so first thing, so we have to store the current chosen edge index for the node I. Actually, I'll be making use of the variable old for this. So let me call the policy of I, actually not j. Let me change this one to I. So next, we have to temporarily switch to the switch the policy to try the another edge. So this one will be policy of I. Let me assign this one to, sorry, let me assign this one to the variable j. Right. So this is fine. This is easy. We are just temporarily switching the policy to try the another edge. Now we need to calculate the mean after switching edge. So we'll be going with a double. So this is fine. I'll just go with the new mean. So this one will be find cycle mean. What are the things? Policy to W and N. The same thing actually. Again, we are making use of the find this one find cycle mean method here. I'll just come out of this one entirely. Now let's move on with the if condition. So what's the if condition states here? If the policy gives smaller mean cycle weight, then we have to update the best mean value and we have to mark that this one. We have found the improvement, right? So these two things we have to do. Suppose if the new mean is greater than is less than best mean, actually not greater than. Yeah. If it is less than the best mean, in that case we have to first we need to update the best mean value. So I'll just go with the best mean equals new mean, and then we have to mark that we have found the improvement. So I'll just go with the improved true, And finally, we have to stop checking other edges for this node. So we have to exit from there. For that, Java provides break statement. I'll just make use of the break statement. Yep. So this is fine. Else, what we have to do? Else, what we have to do? Uh, else, we have to revert back to the original node since no improvement. So I'll just go with the policy of I. So I'll just assign this one to the old. Yep. So this is fine, I believe. So let me format the code so that the code looks good actually. Yep. So we have 1 second. Did I miss anything? Yeah. So this is it for the algo actually. Or have I missed anything? So we haven't written anything right yet. 1 second. Did I miss anything? So we are left with a few things. So I'll just come here. So let's do one thing. So we have to calculate the final minimum cycle mean after the policy stabilizes. After if we have found the improvement after improving the policy, after considering all the cycles, we have to consider the minimum from that, right? From all the cycles, we have found the mean value. From all the mean values, we have to find the minimum value. For that also, we have to write the code, right? So I'll just go with, sorry, let's double, not do. Yeah. So this one will be answer equals find cycle mean. So this one will be policy to WN. Yep. So this is fine. We have to print the minimum cycle mean. For that, I'll just go with the out.println. Out.println. Let me go with minimum cycle. Yeah. Minimum cycle mean. So this is fine. Yep. So this is also fine. So we have successfully print the minimum cycle mean, and finally we'll flush the output buffer. For that, I'll just go with a out dot flush. As we are making use of the print writer, you can just go with a flush or close. Either of them works, right? So we just have to get the output suddenly after this one for all the inputs, right? Suddenly after running the code actually. For that, we'll be making use of the flush or this one close. So this is fine. We are done with the coding part. So let me format the code. So this is it for the algo. Yeah, this is it for the algo. One helper method we have made use of nothing but find cycle min. So we have used it twice within the main method. The same thing actually. Yeah. So the steps that we had discussed during the algorithm of this one, initializing the policy, then the second step, then improving the policy. So that if you remember, implementation is really easy for the Howard's this one. What do we call Howard's algorithm? It's extremely easy. Yeah. So if you understand the algorithm, implementing this one in the form of code is a piece of cake, becomes piece of cake, or it will be very easy, right? So when I say very easy, I'm not saying you'll get it everything, but if you will get to know that these are the steps that we have to implement. If you know the 4 or 5 steps that we need to implement within the this one code, if you are solving certain problems and problem, and if you want to implement the Howard's algorithm, and these are the 4 or 5 steps that we need to implement, and if certain all this one optimization is required, right? So accordingly with the constraints and the problem that we will be implementing, that's it, we are done with that. Yep. So that is the reason, make a note of it. What are the points that we need to remember? What's the algorithm states, mainly the definition part, so that we get to know certain things initially, and then what are the things that we need to implement. These things if we know, it will be very easy to implement the same thing in the form in the problem actually, in the form of problem actually, whatever they have asked. So certain optimization or tweaks will be needed, right? So that we will be doing, right? Every problem, so suppose the constraints are very tight, in that case the optimization will be needed. So in that case we can just go for the this one. If you know the data structures pretty well, if you can just implement, or you can just consider the good data structures, that's it, right? So this is fine. We are done with the algo part. Yeah. So let me run the code. I'll just come here. Let me run the code. So I can clearly see here. Yeah. Minimum mean cycle we are getting here 1.66 this 17. Yeah. So just give me a second here. So we are getting the wrong answer here, right? So we have to get the output 1. So the same example that we have considered here, right? So let me do one thing. I'll just minimize this one. So here, so accordingly with this, see, we will be getting the this one, what do we call, mean from the cycle. So after detect, we will be having more than one cycle, right? So we might have more than one cycle, who knows, right? So we can have 5 cycles, 6 cycles accordingly with the input, right? Either we can have 10, 15 cycles if the this one a number of inputs are large, right? So if the input is large actually, right? In that case, we can have 15, 20, 25, 30 cycles, right? So in that case, we have to find the minimum. We will be applying this formula and we'll be finding the minimum. After finding the minimum, so we might have different cycles. We have to consider all the values and we have to take the minimum, right? So that I have completely forgotten. That is the reason we are getting the this one wrong answer. Let me paste this one. So this is nothing but best equals math.min of this one, best comma mean. So let's do one thing. The same thing here. This is showing error because we haven't initialized this one at all, right? So I'll just go with this one. Best equals. I have just initialized this one to the maximum value. Yeah. Let me leave the space so that this looks good. Let me format the code. Now let me rerun the code. What happened here? One second. Oh, we have to go with the mean as well, right? So let's do that. So I'll do one thing. Instead of return, I'll just go with double here. So this one I'll just go with a variable mean here. So that error will be gone here. So let me format the code once, and this one also. Let me change this one to best. Actually, we have to get the best value or the minimum value actually from all the values that we have found from the cycles, actually from all the mean values that we have found from the each cycle. So I'll just mention best here. Let me format the code again. Let me rerun this one. Yeah, this time we are getting the correct output. Minimum cycle mean is 1.0 or 1 actually, accordingly with the approach. In the approach, we considered the same example. We have discussed this one step by step, right? So we are getting the correct output. Yep. So that was the mistake actually. So here, the formula what I had written, it is correct actually. It would go with the this one. If only one cycle is present, in that case, it is correct. So the code will be correct. What if this one? Many cycles are present and we have to consider the minimum value. That's the edge case, right? So we have to consider that one at any cost, right? So this is fine. We are getting the desired output here, right? So we are getting the desired output. So this is fine. We are done with this part. We are done with the algorithm. Next, what shall we do? Let's do one thing. Now, as we are done with the algorithm, let's discuss the this one, what do we call, complexities part very quickly. The time complexity and the space complexity. Just give me a second here. One second. Yeah. So this is fine. So yeah, what will be the time complexity here? Time complexity. One second. Yeah. The time complexity would lead to big O of V into E into iteration. So this one will be V into E into iterations, right? I is nothing but, I'll just write here ITE. ITE is nothing but the iterations. Just remember this. So why it is big of V into E into iterations? So here V is nothing but vertices checked for the improvement, right? So vertices we are checking for the improvement because individual vertices we are checking for the improvement, so that if possible we have to improve the this one, what we call policy actually, right? So we have to improve the policy every time. If we get the smaller value, we have to consider that value. Yeah. So we have written the code in that particular way itself. So V is nothing but the vertices checked for the improvement. E is nothing but the possible outgoing edges. So the outgoing edge that we consider is nothing but the possible outgoing edge, and iterations is nothing but the policy improvement steps, right? So within the code, we have written the policy improvement steps. We have implemented the policy improvement steps. So overall time complexity would lead to, or it, yeah, it depends on big of this one, vertices, edges, as well as the iterations, big of V into E into iterations. So yeah. So one more thing, Howard's algorithm, whatever we have written, it usually converges very fast in practice. Yeah, comparatively with the Cobb's algorithm, it is extremely faster. Yeah, it converges very fast in practice. Just remember this one. What is the space complexity then? Space complexity would lead to big of V plus E. Yeah, space complexity would lead to big of V plus E. When I say space complexity big of V plus E, so here adjacency storage is nothing but, yeah, adjacency storage is nothing but big of E, right? Adjacency storage is nothing but big of E. And we are making use of the policy array and visited array and policy array and visited array, that would lead to big of V, right? So that would lead to big of E. So overall, this one will be what do we call this one? Big of V plus big of E. So overall space complexity would lead to big of V plus E, right? So the time complexity and the space complexity for the code that we have written would lead to big of V into E into iterations and big of V plus E respectively, right? So this is it for the algorithm and this is it for the complexities part as well. So we are done with the algorithm completely. Now let's do one thing. Let's solve one problem where we can implement the this one Howard's policy iteration algorithm or Howard's policy iteration minimum weight cycle algorithm. Yeah, let's do that quickly. So let's do one thing. Let's continue with the problem part. Yeah. So this is one of the problem where we can implement the Howard this one. What do we call? Howard's policy iteration algorithm or minimum weighted cycle algorithm. So the problem name is maximizing your winnings, right? So you can just go through the question. It's very easy to understand. It's medium to hard based question. Yeah. So you can, if you understand the problem, you can easily implement this one using the, usually you can, we have two ways. You can go with a pure DP, right? Or you can just go with a for intense optimization. You can just go with a Howard's minimum cycle, Howard's policy iteration along with the DP. Yeah, you can use both. So as we have just discussed the Howard's this one algorithm, so let's implement the same for this particular problem. First, let's go through the question. You can just go through the question. I'll just summarize the question so that it will be easier for us to solve the problem. Yeah, let me do that. Just give me a second here. 1 second. Yeah, so this is fine. Yep. So here, first thing, so we will start in room one, right? So we will start in room one, nothing but the index zero, right? Nothing but index zero with zero money. Yeah, with zero money. Again, let me tell you this one. We will be starting in room one, nothing but index zero with zero money. Each turn, sorry, you may stay or we may stay in the same room, right? Each turn, yeah, each turn that we during the play, each turn we may either stay in same room, or we can move to adjacent room. Yeah, either stay in same room, I'll just write here SR, or we can move to the adjacent room. So this is what they have given. Either we can stay in the same room each turn, or we can just move to the adjacent room, earning the value from the matrix, earning the value from the matrix weight of ij. Yeah, earning the value from the matrix weight of ij. This is fine, I believe. Yep. We must make exactly t turns. Yeah. So this is very important. We must exactly make t turns. Yeah. That's what they've strictly asked in the question. Yep. We must make exactly t turns. For every game, what we need to do, we have to compute or calculate maximum and minimum this one money obtainable after t moves, right? So what we need to do for every turn, right? So for every turn, what we need to calculate actually, we need to calculate maximum and minimum money. What we need to calculate again, max and min money, right? So this is fine, I believe. Yeah. Again, let me tell you, for every game, we have to compute maximum and minimum money obtainable after t moves, right? Obtainable after T moves, right? So this is it for the question, right? So one more thing I want to tell you here is the rooms form a complete directed graph where each move adds the edge weight. So graph I'll be showing you later during the approach part. Just remember this. For the rooms form a complete directed graph when we are applying the or when we want to apply the Howard's policy iteration algorithm. So we have to make sure that we will be dealing with the directed weighted graph only, right? So if we are not given weights, we cannot. If the graph is undirected, then also we cannot. Yeah, it has to be strictly directed weighted graph if you want to implement the Howard's and also the Karp's algorithm. These two algorithms are applicable or applicable for the directed weighted graphs only. right? So the rooms form a complete directed weighted graph where each move adds the edge weight, where each particular move, the particular move that we consider adds the edge weight. Yeah. So this is it for the question. Actually, this is it for the question. So just give me a second here. What happened to this one? Yeah, I'm not able to. Yeah. So what's the question again? So let me summarize this one quickly. We start in room one, nothing but index zero with zero money. This part. Yeah. Then each turn we may stay in the same room, or we can move to the any adjacent room, earning the value from the matrix weight of ij, nothing but w of ij. This part. Next one, we must take exactly t turns. Yeah, we must take exactly t turns. Yeah, they have strictly mentioned in the question. For every game, we have to compute or calculate the maximum and minimum money obtainable after t moves. Obtainable after t moves. Yep. So the rooms form the complete directed graph where each move adds the edge weight. What we need to find for every game, not for every turn here, for every game actually. Yeah. For every game, what we need to do, we have to calculate minimum and maximum money. That's what we have to do, obtainable after t moves or the t turns. Yeah, again we have to compute the minimum and maximum money for every game, right? So that's what we have to remember. Yep. So this is it for the question. It's as simple as that. Yep. Let me delete this one completely, so I can just go through the question again. So in the question, one second, this is the input actually. So we have been given two inputs. You can clearly see this one. Yeah. 3, 2, 17, 11, 7, 1, 8, 11, 18, 19. So these are the edges actually with the weight actually. 2, 17, 11, 7, 1, 8. Edges 2 to 17, 7, 1, this one 11, 18 with the weight 19 actually. Yeah, and 1. So this is also one of the input, right? So this is fine, I believe. We have been given two inputs. The output that we need to get here is nothing but 17 to 42 as well as the 0. It's as simple as that. Now, we have we are having complete idea on the question, right? Next, let's do one thing. Let's do one thing. Yeah. Let's discuss the approach for the problem. Yeah. So then we can just write the code, whatever we had discussed in the approach, whatever we will be discussing in the approach, we can try to articulate the same thing in the form of code. And if everything goes well, if we get the desired output, then we can just this one, then we can discuss the complexities for the code that we have written. First, let's discuss the approach as usual. Yeah, let's do that. So let's move on with the approach part. Yeah, so I have considered the first example that they have given in the question, or the first input. Yeah, there were two inputs if you remember within the question. I have considered the first one actually. Yeah, so here let me show this one in the question itself. So this one I have considered. Yeah, 1 4, 1 until 1 actually. Yeah, so this is the first input. We have to get the output 17 to further. Yeah, so let's move on with the further things. So here this input, meaning we will be we are given n equals 3, meaning so this is number of rooms. Yeah, number of rooms is 3, and matrix of w of ij, they have given this one 2 17 11 7 1 8 and 11 18 19. Nothing but money earned when moving from I to J. So this is the money earned when moving I to J. 2 17 11 7 1 18 11 18 19. So T equals 1. Um, the first move will be t equals 1 when t equals 1 actually. Yeah, so let's move on with the matrix here. So 2 17 11, the same thing, 7 1 18 11 18 19, the same thing I have mentioned in the correct way. So this is nothing but from to 2. So t equals 1, t equals to 2, t equals 3, right? So this is the matrix. This one, we have the first row, second row, third row, first row, first column, second column, third column. So the value will be 217. So this will be helpful when we move on with the further things actually. Yeah, so this is fine. We'll start from the room 1. Yeah, so 1 second. So we'll start from the room 1. Yeah, we'll start from the room 1, nothing but the index 0. Since here initially t will be 1, right? So we have already discussed this one. We'll start from the room 1, index 0. Since t equals 1, we only make one move, right? So initially t will be 1, so we will make only one move. So the possible moves will be 1, this one 1, that will be 2, 17 or 11. Either it can be 2, either it can be 17, or either it can be 11 possible moves. Yeah. So maximum will be out of this one, the first row that we have considered, the maximum will be out of max of 2, 17, 11 will be 17 itself, right? So the maximum is 17 and the minimum is quite obviously among this one 2, 17 and 11, minimum is 2. Yeah. Output is 1, 7 and 2 respectively, right? Output is 1, 7 and 2 respectively. Next, let's move on with the graph. So graph rooms can be visualized as the directed weighted graph. So this one we have already discussed, right? So while discussing the question itself, I have said the same thing, that we will be visualizing the rooms as the directed weighted graph. Yeah. So as we are dealing with the Howard's algorithm, we have to make sure that we are dealing with a directed weighted graph itself. Now we are visualizing the rooms as directed weighted graph. See, from 1 to 2 edge, so with the weight 17, we have from 1 to 1. So this one, don't get confused, what is 1 to 1? So this is self loop. Instead of writing in this way 1 to 1 the arrow mark, I have this one written one more node and I have just shown that one, right? So this is nothing but the self loop 1 to 1. So I can just draw the loop there itself. That's also fine actually. From 1 to 1 we have the weight 2, from 2 to 2 we have the 18, from yeah, from 1 to 2 we have 17. Yeah, here you can clearly see from 1 to 2 we have 17, and from 1 to 3 we have 11. This part, from 1 to 3 we have 11, and 3 to 3, this is self loop actually, nothing but 19. We have three self loops, 1 to 1, 2 to 2 and 3 to 3. One self loop with the weight 2, second self loop 2 to 2 with the weight 8, so 3 to 3 with the weight 19, right? So here that's what I want to say. Here self loop exists and the edges are nothing but 1, 1, 2, 2 and 3, 3 respectively, 2, 1 and 19 respectively. So accordingly with the graph that I have shown you, so staying in the room also earns money, right? Staying in the room also earns money in the sense, so the self loop that we have that I have shown you, that through that also we can earn the money, right? Staying in the room also earns money, right? So this is fine, I believe. It's simple. What's the core idea here? So if we do simple DP, so we will be making use of the DP, right? So DP of step, individual step that we consider, and the room that we are in. DP of step into room, so is equivalent to the best money reaching that particular room. That money reaching that particular room, right? Transition would be, so you just have to so we'll be making use of this. Just look into this. DP of k plus 1 into j is equivalent to the maximum of DP of k into I plus weight of I into j respectively, right? So here t can be large. So in our case, we started with t equals 1, but t can be extremely large. So DP alone will be expensive. In that case, DP alone will be expensive. In our case, for this particular input, it is fine, right? So T can be large, so DP alone will be expensive. So we will be going with the Howard's, this one, what do we call? Howard's policy iteration algorithm, or Howard's policy iteration minimum cycle weight algorithm, or minimum weight cycle algorithm. So this is fine. Minimum mean cycle also we call, or minimum weight cycle also we can call. Yep, so this is fine. So the main idea or the key idea is, for very large steps, when the value of t is very large, best path will be equivalent to the cycle mean into steps plus transient value, right? Best path will be going with this, nothing but the cycle mean into steps plus transient value, right? So you have to remember this part. Yeah, best path is equivalent to cycle mean into steps plus transient value, right? So what are the steps that we'll be going with? See, within the Howard's this one policy iteration algorithm, we have already discussed the algorithm. Let's brush up. So what are the steps that we'll be making use of? Yeah, just give me a second, 1 second. So yeah, here 1 second, what is this? Let me close this one. Yeah. So here, the main steps are, first we will find the best cycle mean lambda using Howard's algorithm, right? So this is not Howard's actually. I might have this one, what do we call? Got confused with the Harry Potter movie. Anyways, so we will be finding the best cycle mean, nothing but the lambda using the Howard's algorithm. So the lambda expression is nothing but it is optimal cycle mean. right? So this is nothing but optimal mean cycle or optimal cycle mean. So however you call it, right? So uh, we'll be finding the best cycle mean lambda using the Howard's algorithm. The second step, we will be running the DP for the few steps, right? So DP alone will not help here, right? So along with the DP, you can go with the DP and optimize. You can go with the intense optimization. You can do that as well. So if you go with the Howard's algorithm, it will be easy, right? The implementation becomes easier, right? So we can run the DP for few steps. Once the gain part stabilizes to the lambda per step, once the gain part stabilizes to the lambda per step, we will be extrapolating remaining steps. What we'll be doing? We will be extrapolating remain steps. So these three things, these three words are very important. Once this one, what do we call? Gain stabilizes to lambda per step, we will be extrapolating remaining steps. So this what it does actually, it reduces the complexity drastically. Yeah, it reduces the complexity drastically. Yep. So this is it for the algo. This is it for the algo. It's as simple as that. So this is it for the algo. Right. Next, what we will be doing. Let's do one thing. Yeah. So we are done with the approach part. So let's try to articulate the same thing in the form of code. Yeah. Let's do that. So let's do one thing. Let's move on with the this one. What part this is? Mm, Coding part actually. Yeah. Maximize your winnings. I'll just go with the yeah. Initially, let's go with this itself. So later we can change the name actually while submitting in the cuties. Yeah. This is fine. First thing. So we will be making use of input output package as well as the utility package, as we'll be going with the this one, different utilities actually. I'll just go with io.star. So this is fine. And also let me go with import this one util.star, right? So this is fine. Within the this one, maximizing your winnings class, first thing, let's go with, or let's declare certain global variable. So I'll just go with the static here, final. So let me go with double here. So let me go with a variable infinity. So I'll just mention this one 1e 15 here, right? 10 to the power of 15. So why we are giving this one? This is accordingly with the constant, this one constraints actually. Yep. So and we have to go with the number of rooms in the current game as well, right? So that for that, let me make use of the variable n. Yep. So this is also fine. The next one is we will be going with the adjacency matrix where W of ij stores the money earned moving from room I to room j. Yeah. So I'll just go with the static here. So this one will be double. So this one will be double. Right. So this is fine. Yep. After declaring the variables, let's go with the, or let's move on with the main method. So I'll just go with the this one. Yeah. Input output exception is not required. Just exception is fine. Yeah. Yeah. This is fine. Within the main method, what we'll be doing? The first thing. So let's go with the buffered reader and the input writer actually. Sorry, print writer. So this is buffered reader, and let me go with a print writer. So this one as well. Instead of PW, let me consider this one out, or you can just go with the PW. Doesn't matter. Anyways, so next what I'll be doing. So let's do one thing. So within the main method, first thing, let's move on with the while loop. So I'll just go with a while here, while of true. In that case, so we will be implementing the DP for fewer steps, and then for the optimization, we'll be going with a suppose the t value might be this one very large, right? For that purpose, we'll be making use of the forwards policy iteration algo. So here, while of true, so we have to loop. We have to consider the loop to process the multiple games until the termination condition. This one we know. So let me go with the n. So here, nothing but we are reading the number of rooms here. So I'll just go with integer dot percent vr dot read line. So this is fine. Let me add the trim as well. Trim because to remove the white spaces. Yeah. So this is fine. Next, suppose if the input is 0, then we have to terminate the program. In this case, if n equals 0, then let me give break here, right? So this is fine. Next step, if the input is 0, then we'll be terminating the program. Then the next step is we have to store the number of rooms globally. Yeah, I'll just go with the n here. So we have to initialize the adjacency matrix as well. So I'll just go with new double of this one, n and n respectively. So we have considered capital N, the global variable. So I'll be going with n and n respectively. After successfully initializing the adjacency matrix, so what I'll do, let me go with a simple for loop here. Int I equals 0, I less than n. Let me go with I plus plus. Yeah, so this is fine. Within the for loop, first thing, so we are iterating over each row of the matrix. So let me consider the string tokenizer that comes from the utility package. So I'll just go with the st here equals new string tokenizer. Yep, of the same thing actually, buffered reader dot read line. So trim is not required here. So let me remove the trim. Yep. So this is fine. Why we are making use of the this one trim here? Because we have to split the input line into tokens. So for that purpose, I am making use of the string tokenizer. The next thing is, let me go with a simple for loop because we have to iterate over each column here. For that, I'll consider the variable j equals 0, j less than n, and j plus plus. Yeah. So within this particular for loop, all we have to do is we have to store the money gained when moving from room I to room j. So I'll just go with w of ij here. So this one, let me assign this one to double dot parse double. So this one is fine of st dot next token, nothing but string tokenizer dot next token. Yep. So this is fine. So after this part, we have to read the number of turns that has been allowed. So I'll just go with p, right? So I'll just go with a variable t. So this one will be integer dot percent of br dot read line. The same thing, trim. Let me include the trim because we have to trim the white spaces as we are reading the number of turns allowed. Then we have to go with this one. What do we call? We have to compute the maximum winnings and minimum winnings using the Howard's algorithm. So let's implement the Howard's algorithm and then we can just make use of it within the main method. Yeah. So I'll just do one thing. So let me come out of this one entirely. Let's do one thing. Somewhere I have done something wrong, I believe. What is the wrong thing that I have done? I don't know. Mm, One second. So let me do one thing. If I'm making use of the for loop, I had to close this one flare bracket here itself. Instead, I'll just remove this one and I'll just remove this one. I had to close this one here itself. Anyways, now let's move on with the further things. Now let's do one thing. Let's write the towards this one implementation so that we can make use of it and make use of it within the main method. So I'll just go with the static here. So this one will be long. I'll just go with the forward solve. So let me go with int t and also let me go with a boolean maximize. Yeah, let me go with a boolean maximize. So within the Howard solve method, so this is the function we are computing for the optimal money after the t turns. We have to do that, right? So we have to return the optimal money itself after t turns. So first thing within the method Howard solve. So I'll just go with double here. Let me make use of the lambda equals, I'll just go with a Howard policy iteration, this one method. So to make use of the Howard policy method, this one, so we have to write the Howard policy iteration method first. Yeah. So this is huge. This is going to be huge actually. Let me do one thing. Yeah. Let me type. So I'll just come out of this one entirely. Now I'll just go with a method static. Uh, so three methods. One is Howard solve, where we'll be solving the, where we'll be implementing the Howard complete Howard this thing calculations within that one. Yep, Howard solve. So to implement certain things, we have to implement the Howard policy iteration first. The first step in the algorithm, if you remember. Yeah, that one we have to do. For that, I'll be making use of the helper method. Then we can just implement. We can just make use of the Howard solve within the main method. These three methods will be making use of mainly. Yeah. First, let's go with the this one Howard policy iteration. I'll just go with a Howard. This one will be policy iteration. Yeah. So I need one parameter, nothing but maximize. Yeah. So if you remember the algorithm, what we'll be doing within the hover policy iteration, first we'll initialize the policy. Then if you remember correctly, then we'll be going with the second step, we'll be performing the calculation, and third one will be, if suppose if we can improve the policy, right? So then we will be doing that, these three things, right? So first let me consider the variable pi here. Let me go with new int of n. So this is fine. Uh, this one is nothing but the policy array. Policy array pi of I, it stores the chosen next node for the node I. Next, let's go with the simple for loop. So this one will be int I equals 0, I less than n. So let me go with the I plus plus. So within the for loop, first thing after initializing the policy greedily, so I'll do one thing. So I'll just initialize on that this way. I haven't done that one yet, right? So I'll just go with a, let me initialize this one to 0, and let me go with a best. Let me consider the variable best here. So if maximize, then I'll just go with a negative infinity. Else, let me go with a positive infinity. Yep, so this is fine. So we have to test all the neighbors. For that, I'll just write one more for loop here. So this one will be int j equals 0, j less than n. So let me increment the. I forgot to plug the charger actually. It completely got switched off itself. Anyways, turned off itself. So let's continue with the same. Now, so where did I leave? Basically, so we were testing all the neighbors, right? So I'll just go with a simple if condition. So let me do one thing. Suppose maximize, then I'll just go with w of I and j. Yeah, if it is greater than best, in that case, I'll just go with a w of I and j. So this one will be w of ij. If it is less than best, not greater than best, we will be checking for less than best. If it is, then in that case, what we'll do, I'll just go with best equals w of ij. Yeah, this one. And finally, p of ij. Yeah, p of ij. So I'll just pi of j, sorry. Let me this one, assign this one to the j, not I. We have considered j, right? But on the for. Yeah, this is fine. This one we are going. Anyways, we are done with this part. So we are choosing the best immediate transition here, right? So I'll just format the code so that the code looks good. So let me come out of this one entirely. Now let's do one thing. Let me go with the lambda. We will be going with the lambda here, right? We'll be going with the lambda because we have to store the optimal cycle mean, right? So as I've said, so I'll just do one thing. Yeah, lambda, let me initialize this one with a 0, and also we need the we need bias vector actually, that will be making use of it on the policy improvement. So I'll just go with the double here. V equals, let me go with new double of size n, right? So this is fine. Next, let's go with a simple for loop. So we have to implement the policy improvement, or we have to iterate through the policy improvement. Yeah, so I'll just go with for int iterations equals 0. So iterations, so I'll just go with this one less than n into n here. So n into n plus 10, right? So let me increment the iterations as well. Yeah, so this is fine. So within this particular for loop, we are iterating through the policy improvement, right? So we have to track the visit states for the cycle detection as well. For that, let me go with visited. Yeah, so this one will be new int of n. Yep. So after doing that, so I'll just go with the two main steps. So let me go with the variable cycle ID equals new int of n. So this is correct. Yep. And also let me initially fill the cycle ID with the all the cycle IDs with a -1. Yeah. So this is fine. Next, we have to store the this one mean weight of each cycle as well, right? For that, I'll be making use of the cycle lambda. One more variable, right? So I'll just go with double cycle lambda. So this is fine. I'll just go with the new double of n. So this is also fine. So next, I'll just go with int num cycles. So this one is equal to 0. And also let me go with the arrays.fill cycle lambda. So this is we are not dealing with a cycle lambda here, right? So we are dealing with a vertex, right? Initially we'll start from the 0. I'll not give infinity here. Initially we'll be starting from the value 0. So this is fine. Then we have to explore the policy graph to detect the cycles. For that, I'll just go with the simple for loop here. So this one will be, I'll just make use of the start. So I'll just go with the start less than n. So let me increment the start. Yep. So this is fine. Let me write the simple if condition here. If already visited, right? So if visited, yeah, if visited of start. So if this is not equal to 0 or minus 1, I'll just go with a not equal to 0 or minus 1 also works, actually it doesn't matter. So if it is not equal to 0, then in that case we have to give continue, right? So we have to skip. So I'll make use of the continue keyword that is provided by the Java. So let me make use of the array list here. So let me go with, as we are dealing with the integer, so let me go with the integer path equals new. So this one will not be this one path new. So this one will be array list. Yep. So this is fine. I'll just go with int current equals start. Yeah. So this is also fine. Yeah. Let's go with a simple while loop. So here visited of current, if it is equal to 0, suppose visited of current, if it is equal to 0, then in that case what we have to do, we will be let's do one thing. I'll just give here visited of current. Yeah. So this is fine. Visited of current, let me assign this one to 1. I'll just go with a path dot add of current. So I have misspelled add here. And finally I'll just assign the current to phi of current. Yep. So this is it. So we have to follow the policy edges until the visited node. That one also we have to do. So let's move on with a simple if condition. Suppose if we have found the new cycle, right? So suppose if we have found the new cycle, I'll just go with a visited of current. So instead of equals 0, if it is equals 1. Suppose if we have successfully found the new cycle, then within the if condition, I'll just go with the variable here. So this one cycle weight. We'll just go with cycle weight. Let me initialize this one with a 0. I'll just go with a cycle length. Let me assign this one to 0 and let me go with a C that is equal to current. Yep. So this is also fine. I'll just go with the do while loop. So within the do, so let me go with the cycle weight here. This part cycle weight is equal to cycle weight plus weight of C as well as phi this part, and also let's go with a C again. Yep. This one is not 1 second. This one will be, yeah, V of C. So this one I'll be closing here. Yeah, this is fine. And also cycle length. So let me increment this one and cycle ID, this one as well. So this one of C. So this one equivalent to num cycles. So this is fine. Let me assign the C to phi of C. This one of C respectively, right? So this is also fine. Yeah. So let me go with a while, as we are dealing with the do while. So let me go with while C not equal to current. Yeah. Not equal to current. In that case, what we have to do, this is it, right? So we are making use of the do while. I completely forgot. Anyways, so we are successfully so we have successfully computed the total weight and length of the cycle. No, we haven't yet, right? So we have written do while. So we have to compute the total weight and length of the cycle. For that, I'll do one thing. So I'll just go with one more variable here, double lambda, nothing but lam. So I'll just go with the cycle weight here. This one cycle weight by cycle length. Yeah, by cycle length. So this is fine. Yeah, I'll just go with a cycle lambda, this part. Yep. So I'll just go with the num cycles, this one. Yeah. So this one equals lambda. Yep. So this is also fine. We are just computing the mean cycle weight. So I'll just go with double here again. So let me go with a running V. I'll just go with a running V. Let me initialize this one to 0 and let me initialize the C to current as well. Yeah. Double running V. We haven't made use of the double running V at all. A running V variable name at all. Sorry. 1 second. Have we? So 1 second. Oh, I haven't left the space here, man. That is the reason we are getting error. The heck. Sometimes. Anyways, so let's move on with the again one more do while. I'll just go with V of C here, right? So this one, let me assign this one to the running V. So this is fine. So I'll just go with the running V again. So this one will be equivalent to W of C. Again, I'll just go with the pi of the variable that we have considered, pi of C, this one minus lambda, right? Minus lambda. Next, I'll just assign the C to pi of C. Yeah, pi of C. This is also fine. So finally, let's write the while loop here. While loop while C not equal to current. Yeah. So this is fine. So we have to compute the bias values for the each node. So I'll just increment the num cycles here. That's more than enough actually. I'll just go with num cycles plus plus. Yeah. So this is fine. I'll just come out of this one entirely now. So let me go with a simple for loop. So this one will be int node of path. So this is fine. So I'll just go with visited of node, this one, and let me assign this one to the value 2. Yeah, let me come out of this one as well. So I'll just go with a this one lambda this time. Lambda, if it is again maximize, then I'll just go with a negative infinity. Let me go with a negative infinity, not the okay. Not the underscore actually, it's hyphen. I'll just go with the else I'll just go with positive infinity here, right? So we are selecting the best cycle. So let's do one thing. I'll just go with for c equals 0, c less than num cycles, and let me increment the c. So I've misspelled the int here. So within the for loop, first thing I'll just go with if condition, if maximize, if maximize, then I'll just go with the cycle lambda, this part of c actually. If it is greater than lambda, then cycle lambda of c uh, less than lambda, right? So then in that case, what we will be doing, so lambda, so I'll just assign this one to the cycle lambda of c. Yeah, this is fine, I believe. So I'll just come out of the if condition. So we'll be making use of the array list, and we have to build the reverse graph of policy edges as well. Right. First, let's go with the array list as we need to save. Yeah. So I'll just go with the integer here. Oh, I'll just go with list. One more list actually. List of integer. So this is fine. So I'll just go with the reverse pi, nothing but rev pi. So this one will be new array list, right? So I'll just go with a simple for loop here. Instead of the start, I'll just go with I 0 I less than n. So I'll just go with the I plus plus. So here, I'll write directly itself. It suppose this one if cycle id of I, so this one cycle id of I, if it is greater than or equal to 0, if it is greater than or equal to 0, in that case, what I'll do one thing. So I'll just go with on cycle of I. So this one, let me assign this one to the value true. Boolean value true. For this, oh, we are not dealing with this one. Sorry, I get confused sometimes. So this one, I'll just do one thing. So let me do one thing. I'll just go with mm, reverse by this one dot add of new array list actually new array list. Yep. So this part. So this is fine as well. Yep. Let me come out of this one entirely. Now let's go with a boolean. This one on cycle. So I haven't initialized. I hadn't initialized at all. I wanted to make use of this one on cycle. Quite obviously, you would have got the error. So this is fine. So on cycle, so I'll just go with a new boolean size n. Right. So this is fine. What happened here? Required type boolean itself. What's wrong? Oh yeah, we have to mention the array here. Right. So now the error will be gone. Yep. So this is fine. This is correct. Let's move on with the further things. Yeah. So I'll just write one more for loop here. The same thing, the same for loop. So here, let me copy this one. Yeah. And let me paste it over here. So this is fine. I'll just go with if cycle ID of I, cycle ID of I, if it is greater than or equal to 0, then on cycle of I equals true. On cycle of I equals true. Next, what shall I do? I'll just go with a q actually. Yeah, let me go with a q of integer. The same thing actually. I'm just going with a array dq, or you can just go with a linked list as well. Linked list works. Array list or array dq also. Right. So it's your choice. Now let me go with boolean here. Yeah, let me go with boolean. Let me go with in q. Yep, in q. Again, it will be of size n. It will be of size n. Right. So this is fine. Let's go with a simple for loop. So this one will be int I equals 0, I less than n. So let me increment the I. So within the for loop, what I'll be doing, I'll just go with a reverse by. So this one, yeah, was by dot get of p of I dot get of instead of I, I'll just go with a pi of I. Yep. So this is fine. Pi of I dot add of I. So this is fine. Next, let me write the simple if condition here. If on cycle of I, if on cycle of I, then what we'll do, we'll go with a q of add of I. So this is also fine. Or let's do one thing. Let me cut this one. Yeah, let me paste it over here. And one more thing is in q, this one we have to set this one to the boolean value true. So let me format the code so that the code looks good. Yep. So now let me come out of this one entirely. If and for loop mainly. Yep. So now let's move on with the while loop. Yeah. So we have to enqueue the cycle nodes, right? So I'll just make use of the while here, while q not empty. Yeah. So this is fine. So I'll just go with int node equals q dot poll. So this is pure BFS if you observe, right? So this is fine. Then let me go with a simple for loop here for int red. So I'll just go with reverse by dot get of node. In that case, I'll just write the simple if condition, if not of on cycle, this part of red. Yep. So I'll just go with, and along with it, we'll be going with in q this time, in q of red. So this is also fine. Yep. So I'll just go with v of red. So I'll just assign this one to v of node. Yeah. So hyphen w of red. So this one will be pi of red. Yeah. So this is fine, I believe. Plus, let's concat let's concatenate the lambda. So this is fine. Next, what we are going to do, so I'll just add this one to the queue. Queue dot add of this one PRED. That's it. So we don't have to go with the PI of PRED. Yep. So this is also fine. Finally, all we have to do is we have to set the in queue. Similar to the previous step, we have to set this one to true. PRED. The that one we have considered, right? The variable in PRED to true. Right. So let me format the code so that the code looks good. So I'll just come out of this one entirely. So within the if condition, I haven't written anything. So these are all the things I have to write within the if condition itself. Anyway, so I'll just go with the, let me paste it over here. Right. So 1 second. Yeah. So this is fine. I'll just come out of this one entirely now. Let me come out of this one entirely. Now we have to propagate the bias values backward. So I'll just go with a boolean here. So let me go with improved. So let me assign this one to the boolean value false. Yep. So let me go with the two for loops here. One is int I equals 0, I less than n, I plus plus. So again, let me go with one more for loop here. So I'll just go with int j equals 0, j less than and j plus plus. So this is also fine. I'll just go with a double. So let me go with current here. So this one will be w of I and j. Instead of the j, I'll just go with pi of I. So this is also fine. Minus v of pi of I. So this is also fine. And also I'll just go with a double here. So I'll just go with a candidate. So I'll just go with CA and D here. W of ij. So minus V of j. So this is fine. So let me write the simple if condition. If suppose maximize, right? So this one will be CA and D in the secondary. If it is greater than current, less, I'll just go with a 10 to the power of minus 9, 1e hyphen 9. So in that case, I'll just go with the can. If it is else, we'll be going with a CA and D less than the variable current that we have made use of hyphen 1e minus 10, 10 to the power of minus 9. Yeah. So in that case, I'll just go with I of I. Let me assign this one to the j, and also improved. Let me assign this one to the boolean value true. So this is fine. Let me come out of this one entirely. So what happened here? Improved. The value true assigned to improved is never used. So this is fine. J improved equals true. So this is fine. Let me come out of this one entirely. Now, if not of improved, so I'll just go with if not of improved. Then what we have to do? Let's break. Yep. So if not of improved, break in the sense here we have to stop if the policy has converged, right? So the policy converge is extremely fast when it comes to Howard's, right? So that is the reason we prefer Howard's algorithm over Cobb's algorithm. Yeah. So just remember this. As the code will be linear and it's if you don't know the algorithm, it will be difficult to implement. People go with the Cobb's rather than the Howard's, right? So this is fine. If not of, then we break. Then I'll just come out of this one entirely. Now, so let's do one thing. So we have all we have to do is we have to return lambda. Yep. So this is it. Extra braces actually. 1 second. So what mistake I have done here is, so here in this case, if I have opened the if condition, I had to close here itself. So that is the reason one extra bracket I have placed here. So let me yeah, now this is fine. The error is gone, right? So let me format the code so that the code looks good. Yep. So this is fine. We are done with the Howard policy, this one iteration. Next, what shall we do? Policy iteration, we can just make use of it within the Howard solve, right? So how we can use, let's see the same actually. So let's do one thing. So yeah, double lambda I have given here, right? So where I have left, we have to calculate the optimal cycle mean using the Howard's algorithm, right? So I'll just go with the Howard policy iteration here. So this part, so this is fine. I'll just go with a maximize keyword. So this is fine. It's as simple as that. Now, after computing the optimal cycle mean using the Howard's algorithm, so if maximizing, we start with a very negative values. If minimizing, we will be starting with a very large values, right? For that, I'll just go with a variable. It's good to make use of the keyword sentinel here, as we are dealing with both this one maximum as well as the minimum, right? So I'll just go with the maximize here. If it's true, then negative infinity. Yeah, we have seen this one already in the Howard's policy iteration. Yeah, you don't have to worry that much. You don't have to worry that much, or else positive infinity. So this is fine. Let me remove the negative this one minus sign actually. Yep, so this is fine. Now, what shall I do? Let's do one thing. We need the DP. Yeah, so we'll be going with the DP for some steps. So I'll just go with a double. So I have to mention the array. Yeah, DP equals new DP of size n. Yeah, size n or not new DP man. So DP equals new double of n. It n has to be capital here, right? So it's the global variable, right? So DP of I, what it does, it stores the best money achievable ending in the room I. Now we have to initialize the DP array with a sentinel value as well. For that, I'll just go with the arrays here dot fill of DP comma sentinel. Yeah, this part. Next, let's assign DP of 0 to 0. So this is fine. I'll just go with a 0 0.0. We are starting in the room 0 with the money 0. So in the question itself, while reading the question, I said the same thing, right? So we'll be starting with the this one. We'll be starting from the, or we'll be starting in room 0 with the money 0. Yeah. Next, let's move on with a for loop here. So this one will be for int step equals 0, step less than t. Yeah, turns actually turns t. Then let me increment the step. So this is fine. Within the for loop, what I'll do, we have to simulate the each turn. For simulating the each turn, I'll just go with a some random variable here, double. So I'll just go with a ndp. So I'll just go with new double of n. So this is fine. We have successfully created the new DP array for the next step. So let's initialize the new DP with the sentinel. Yeah. So we have already considered the sentinel variable, right? So let's do that. Array dot fill here. This one ndp with the sentinel. So this is also fine. Let's move on with the other things. We have to iterate possible destination rooms as well as we have to iterate current rooms. Yeah. So let's go with the two for loops here, nested for loop. So I'll just go with int j equals 0, j less than n plus plus. Here this is fine, and again for here the same thing, I equals 0, I less than n I plus plus. So within the for loop, so we are iterating the possible destination rooms, or and we are iterating through the current rooms as well. So within the for loop, we have to skip if the state was unreachable. So for that, I'll just go with the if. Suppose if dp of I, suppose if dp of I is equal to sentinel, so in that case, what we have to do, all we have to do is we have to skip. So I'll just make use of the continue keyword. Yeah. So now we have to calculate the profit if moving from room I to room J. So I'll just go with the double here. So this one will be val. I'll just go with the dp of I plus weight of I. Yeah, so this is fine. So we are just calculating the profit if moving from room I to room J. So now we have to choose better values depending on maximize or minimize case. So for that, I'll just go with if here. So this one is fine. Maximize. Then let me go with the val. If it is greater than ndp, new dp of J, then in that case, if not, then let me go with the value less than. We will be checking whether the value less than ndp of J. Yeah. So this is fine. Yep. We are choosing the better value depending on the maximize or minimize case. Yep. Now let me assign new dp of J equals this one ndp of J to value. So I'll just come out of this one entirely. Now let me format the code so that the code looks good. So this is fine. Let's continue with the further things, right? So we have certain things to do. So this will be huge again. Anyways, now let's do one thing. So we have to assume the gain per step has stabilized or not. For that, I'll just go with a boolean. Yeah. So let me go with settled. Yeah. Equals true. This is also fine. Then we have to check the this one stabilization condition. For that, I'll just go with for here int I equals 0, I less than n. Let me go with a I plus plus. So here within the for loop, what shall I do? I'll just go with the if ndp of I, if it is equivalent to sentinel, then I'll just hit the continue keyword. Nothing but let's skip from here. So this is fine. Then let's go with a simple if condition. If dp of I, if it is equal to sentinel, then what we are going to do, I'll just go with the sentinel, not settled actually. Sentinel. So this one, let me assign this one to boolean value false. Yeah. What happened here? Provided boolean. So, oh yeah, this one is settled itself. I got confused with the keyboard actually. Sentinel just now I had used the same thing, right? Not the Sentinel actually settled. So we have to exit from here. So I'll just give break. So let me come out of this one again now. So if the previous step is unreachable but current reachable, but the current one is reachable, then also it is not stable. For that also we have to write the condition. I'll just go with the if here math dot this one absolute nothing but abs when dp of I minus here instead of the sentinel I'll just go with this one dp of I, right? Dp of I, so this one not less than sentinel, dp of I minus, let me go with a lambda, right? Lambda, so this is also fine. So let's check whether let's do one thing. Math.abs, so I'll just do one thing. Let me go with one more parenthesis here. Let me add one more parenthesis here. So let's check it whether it is greater than 10 to the power of minus 6, nothing but 1e minus 6 here. So this is fine. So within this if condition, I'll just go with let me assign the settle to false here. So this is fine. And let's break out from here. Let's exit from here, right? So this is fine. Yep, let me come out of this one entirely. Now we have to move the DP to the next iteration. DP equals new DP. So this is also fine. So after moving DP to the next iteration, if the stabilization is detected, so I'll just go with if of settled. So then in that case, what we'll be doing, if the stabilization has detected, in that case, I'll just go with int keyword remaining equals turns t minus 1 minus step. Yeah. So I'll just go with a step here, right? So this is also fine. We are just computing the remaining steps accordingly with the algorithm. So suppose if remaining, if it is greater than 0, then in that case, what we will be doing, so I'll just go with a simple for loop here. Int I equals 0, I less than n. So this is also fine. Again, I plus plus. So here in this case, let me write the if condition here itself. If suppose dp, suppose dp of I, if it is not equal to sentinel, in that case, what I'll do, I'll just write here dp of I equals dp of I plus lambda into remaining, right? So this one is easy to understand. We are just accordingly with the algo, if you remember, we have to, I said we will be extrapolating remaining steps using the cycle mean, right? So that's what we have done here within the this one, this if condition actually. Yeah, this is fine. Let me come out of this one entirely now. I'll just give break. We have to exit. So I'll just make use of the break and let's continue with the further thing. So this is huge. Anyways, so we have to store the best result among the final states. Meaning, so here in this case, if we have got the several cycles and we have to choose the minimum from that cycle if you know the algorithm pretty well. So the same thing will be implementing here. So I'll just go with the double best equals, let me give maximize here, right? So I'll just go with the this one, not underscore, negative infinity, or sorry, what happened here? Else positive infinity. Yep. So after this, let me move on with this one for loop. So I'll just go with a double here. Let me consider individual vertex of the DP. So this is fine. Let me write the simple if condition. So I'll just go with if v not equal to sentinel this part, and let me go with maximize here. This is also fine. If true, then v will be checking if v is greater than best. If it's false, then we'll check whether v less than best. Yep. So this is also fine. In that case, I'll just assign best to v. Right. So this is fine. We have just selected the optimal value across all the rooms. Finally, we have to round the result to the nearest integer. So I'll just make use of the math dot round. So yeah, I'll just go with math dot round of this one best actually. Yeah, let me pass the best variable as we are storing in the best variable itself. I'll be going with the best. It's as simple as that. Now we are done with this part. Yeah, we are done with this method. Forward policy iteration. Previously we were done with the forward policy iteration. Now we have made use of the Howard policy iteration inside, and we are done with the Howard solve. Main Howard's algorithm we have implemented. Yeah. So we have implemented it. It might find huge actually. Yeah. This is huge. I'm not gonna say no. If you know the this one algorithm correctly, the implementation becomes easier. Right? The implementation becomes easier. That's what I want to say. So mainly the people try to go with the carbs. They ignore the Howards because the implementation is quite difficult compared to CARPS. Yeah, CARPS is this one. You'll be going with a less code, but it is somewhat slower, right? It is somewhat slower. This one, the convergence in the Howard, this one algorithm is extremely fast, and the algorithm is uh, faster than the COPS algorithm as well. Just remember this one, these 2 points. Yeah. So if extreme this one intense optimization is needed, or the extreme optimization is needed, in that case, even if the COPS algorithm is failing, in that case you can go for the forward, right? Just remember this one. Both solve the same problem. Both solve the same problem, but the implementation is different, right? COPS, this one minimum mean cycle, and this one Howard's policy iteration minimum mean cycle algorithm, both solves the same problem, but the implementations are different. Now let's move on with the main method. Yeah, where we had left, I have completely forgotten where we have left actually. So here, just give me a second here, 1 second. So we are going with the int equals integer dot parse and this one trim, right? So this is fine. Oh, we are left with only one step, nothing, but we have to compute or calculate the maximum winnings and minimum winnings using the same algorithm, nothing but we have purely implemented the Howard's algorithm here, right? Or Howard's policy iteration algorithm. So policy iteration involves certain steps. We have made use of the this one. What do we call helper method for that? Now we will be implementing, or we will be making use of it within the main method. Yeah. So I'll just go with out here, out.println. So let me go with println. As we are going with a print writer, we'll be directly going with out.println here. So let me go with a Howard solve of t comma true, right? So this one will be t comma true. So this is fine. Yep. It's as simple as that. Next, I'll just go with, so this one. Plus, I'll just go with the Howard solve. This part, Howard solve of t comma false. Yeah. So this is also t comma false. This is fine. Finally, we are left with only one thing. We have to flush the output buffer. For that, I'll just go with out dot flush actually. You can go with either of them, out dot flush or this one close actually. Either of them works, right? So this is it for the what do we call problem. right? So yeah, this is it for the algo or the problem. Let's do one thing. I hope we do not get any error. The solution is huge actually. The code is huge actually. I won't be like. Anyways, so now let's do one thing. I'll just come to the problem part. So let me copy this one entirely. So I'll just open the IntelliJ. So let me run the code. I hope this works. Where semicolon? Yeah, let me give semicolon here. Let me rerun this one again. Yeah, so this is working. Let me provide the input. Index 1 out of bounds. Okay, somewhere mm, we have not mentioned, or we have mentioned the wrong this one size actually. Let's check for the same. So let's do one thing. Let's check where we have done wrong. Let me minimize this one. So I'll just let's see. I'll just come to the Harvard policy iteration part here. So PI of, oh, this one has to be PI of I equals J. We have to assign this one I to the J, not J to J itself, right? So this is fine. Mm, so this is fine. Next, if I have done anything wrong, let's check for the same actually. Yeah, one thing. Yep. Yeah. Mm, so instead of the current, I'll do one thing. I'll just go with the current value here, right? So this is fine. Or this is not required at all. So this, let it stay current itself. So this is fine. So and let we are this. So this one W of we don't need PI here, right? So we just need I and J, IJ minus VJ actually. Let me remove this one. Yeah, let me remove this one as well. Yeah, so this one is fine. Let me format the code once. So these are the mistakes I believe. Do we have any other? Do we have any other? Let's check for the same. It's fine. Fine. This is fine. So here, if I have done something wrong, 1 second. So I have considered here for int I equals 0, I less than n. So we are considering for all the nodes. So this is fine. Suppose I have written, this is fine, I believe. Mm, New RLS. So this works actually. So here I have written the same if condition itself is not required actually. I'll just go with a pi. So this one I'll just go with dot add. So here of new array list actually. Yeah. So this is fine I believe. So let me format the code. Now let's do one thing. Let me run. So I'll just go to the Chrome. So let me copy the this one input. Yeah, and let me paste it over. Yeah. Now we are getting the correct output 17.2 as well as 42.0, right? So let's check the same. We have to get 17.2 as well as 42.0. You can clearly see here, right? So those were some of the corrections actually. Yeah. So here I have written the same if condition, I think. So I got confused and I while typing I had typed the same thing. So this is fine. So yeah, here you can check. So let's check 17 to 42 and 0. So this is the output that we need to get, and we are getting the correct output. Let me do one thing. Yeah. So let me copy the same thing here. Yeah. Let me copy the same thing, and I'll just come to the Chrome. So I have already this one. I have already chosen this one Java here. Let me click start coding. Let me paste this one over here. So let me do one thing here. I'll just remove this one package out. So this is just for the this one IntelliJ, right? And also I'll just go with the let me remove this one and let me go with the name game show. Yeah. So this is fine, I believe. These are the two things that I have to change, right? So while submitting. So let me submit this one now. I hope no other changes are required. Yeah. So this is fine. Let me hit the submit button. Let's wait for some time. You can clearly see here running. I hope this gets passed. Yeah, you can clearly see here. This got accepted runtime 1.14 seconds. So whatever the code that we have written works absolutely correct. So we have successfully implemented the Howard's policy iteration algorithm. Yep, the Howard's policy iteration for the minimum mean cycle, or yeah, minimum mean cycle. So whatever the code that we have written works absolutely correct. So we are done with the Howard's policy iteration algorithm. I hope the algorithm part is completely clear. See, the algorithm is little bit lengthier. If you know the algorithm pretty well, implementation of the algorithm becomes easier, right? So that's what I say every time. So try to get to know the algorithm. So then if you know the algorithm pretty well, if you know what you're doing, so while implementing, while I show the graph part, actually graph part and the theoretical part, apart from that, when we discuss the approach during the algorithm part, so we have to pay attention there. So if we know that part, actually implementing that one within the code is not a big deal, right? So implementing within the problem, sometimes you might not get the output, but your this one, what do we call, your implementation, or whatever the code that we have written, so it becomes easier to implement, right? Might be you might make mistakes while typing and other stuff. You can debug that one later, because the code is huge for this particular, this one, what do we call, to implement this one becomes, the code is heavier, actually. That's what I wanted to say. Anyways, so this is fine. Yeah, we are done with the this one, Howard's policy iteration minimum mean cycle algorithm. And again, so these two algorithms, usually when the problems are asked, there are very less chances that these kind of problems are asked. So if they have asked the problem, if suppose if there is a problem and you want to implement, just consider both of them. See the constraints, and you have to know the complexities part as well, right? So you have to know the complexities part. Yep. So you have to know which one to implement. Usually, again, I'm saying this one, I'm stressing on this one. Howard's algorithm is faster than the Cobb's algorithm comparatively, but Howard's algorithm is difficult to implement. Right? If you know the algorithm, you can implement easily, but the algorithm is huge comparatively to the Cobb's algorithm. So people choose the Cobb's algorithm just because it is easier to, it's not because it's easier to implement. The amount of lines you have to type is less. Yeah, the code will be less and it will be easier to debug. That is the reason people choose Cobb's over Howard. But if the constraints are extremely tight, and if you want to implement the Howard, you have to know the algorithm pretty well. So that is the reason I say every time you have to this one, we have to know the algorithm pretty well. If we know the algorithm pretty well, implementation becomes very easy, right? However large the code is, so implementation becomes very easy if you know the algorithm. Yeah, that's what I wanted to say. We are done with this part. You can clearly see here we got AC, right? AC in the sense we got accepted here, right? So we are done with this particular part, right? So we are done with the part. Again, Howard's algorithm is faster than CARP, and CARP is little bit slower, but CARP's algorithm is easier to implement rather than comparatively with the Howard's algorithm. Just remember these two things. Yeah. So one more thing, let's discuss the complexities for the code that we have written. Let's do that. Yeah. 1 second, just give me a second here. So yeah, so what will be the time complexity here? Just give me a second, 1 second. Yeah, what will be the time complexity here? The time complexity for the Howard's algorithm would lead to big of n cube. Yeah, the time complexity for the code that we have written due to the whole this one Howard's algorithm would lead to big of n cube. And about the DP phase here, right? The DP phase, we have made use of the DP, right? So DP alone will, it's not possible to this one, what do we call, uh, just make use of the DP and solve this particular problem. Even if you want to go with only DP, you have to go with the intense optimization. You have to use certain things. So it's better to use the Howard's algorithm here, right? So this is fine. So for the Howard's algorithm, it is big of n cube. And for the DP phase, so I'll just write here for the Howard's, it is big of n cube. For the DP phase, it is nothing but big of t into n cube, right? T into n square actually. Yeah, t into n square, right? So but stops early after stabilization. It stops very early, just after the stabilization we are stopping the DP. So overall time complexity is dominated by the Howard's algorithm, and it is almost equivalent to big of n cube, right? Big of n cube. So in our case in the code we have made use of the variable big N actually, right? Capital N, sorry, not yeah, big N or the capital N. So overall time complexity would lead to big of n cube. So what will be the space complexity here? Space complexity would lead to big of n square. You would have already guessed, it would lead to big of n square. Why it is big of n square? See, let me tell you one thing. So we are making use of the matrix storage, which leads to big of n square. So I'll just write here matrix storage, nothing but ms, and we are making use of the DP arrays as well, which would lead to big of n, right? This one, let me write here DP array. Yeah, let me write the DP array. DP array, this would lead to big of n. Yeah, big of n. So total, so this one matrix array will be dominant. Matrix storage will be dominated here in this case. So overall space complexity would lead to big of n square. Yeah, the time complexity and the space complexity for the code that we have written would lead to big of n cube and big of n square respectively, right? So big of n cube and big of n square respectively. So this is it for the coding part. Yep. So let me do one thing. Let me delete this one. Yeah. So this is it for the coding part, and yeah, this is it for the coding part, and this is it for the complexities part as well. So I hope Hogwarts algorithm, sorry, I remember Harry Potter every time. I hope Hogwarts algorithm is completely clear, and we have successfully implemented the algorithm in this particular problem as well, right? So yeah, next, what we are gonna do? Let's do one thing. Just give me a second here. Next, we are gonna discuss about the directed Steiner tree. Right? It's one of the well-known algorithms as well. Next, we are gonna discuss the directed Steiner tree. For now, this is it. Thanks for watching, guys. One